Let us continue with the story of polymers. Physical properties of polymers. You know what physical properties are, right? Like boiling point, melting point, solubility, viscosity. Those are the physical properties we might want to define, okay? So the physical properties are controlled by the size of the polymer chain and the nature of the side groups, especially in the vinyl monomer that we just talked about. Remember, vinyl just means carbon double bond carbon. That's a vinyl. This is a vinyl. This is just a substituent of the vinyl. So if you want to define the physical properties, you really have to consider the size of the polymer and what the side chain is. For example, in vinyl polymers. Thermoplastic polymers are polymers that can be recovered or reformed when heated to melt. Okay, so once you cool it down, it retains its physical structure. Okay, you heat it, it deforms, you cool it, it reforms. So there's deformation and reformation by heating of this polymer. Some polymers, when you heat them, they're gone. For example, if you try to heat a peptide, which is a polymer made of amino acids, it's gonna die. That's why enzymes are denatured by temperature. But there are polymers which can be denatured and renatured. Those polymers are called thermoplastic. Okay, so thermo stands for heat. So the effect of heat on this polymer is not bad, because the polymer can recover itself, can recover its structure. The process of heating can be repeated so many times without the polymer getting destroyed, and that's why they're used to make materials in material science. Okay, the other thing we can talk about is cross-linking between polymer chains. That's done by adding divinyl monomer. Like I said, this is a vinyl group and this is a vinyl group. Okay, so it's a divinyl monomer. So if you use styrene, this guy, to make a polymer, obviously it's gonna undergo radical process. Okay, so allow me to abbreviate the ring to be a phenol pH. So in this case, this is the structure of the polymer you'll get. Okay, this bond means you can continue to the left and to the right, and of course it's gonna be repeated n times. So notice that structure is this structure, only that here we've shown how many monomers? We've shown 4 monomers. This part right here, okay, is this divinyl monomer. So it tends to link one polymer with another one. Okay, so if this were to make a polymer, that's what it will be, but this inserts itself as one of the monomers during the mechanism. It gets inserted onto one polymer within its structure, which again, because there's a vinyl down here, this will also insert itself into another polymer at the bottom. That's what we call cross-linking. Now, what if you were to use glue? You are to use vinyl alcohol, which is not possible. You learn that in the lab. Assuming this is what would have been the monomer, one would have made this alcohol. Like I said, the vinyl alcohol usually does not exist. You learn that in the lab. The reason being, it stays as in the aldehyde tautomer form. We did tautomerism, so the vinyl does not exist. But there's a way we make glue through vinyl acetate, then hydrolyzed to give you vinyl alcohol. Those taking the lab will learn about this. So this is actually glue, the structure of glue. Okay, it's glue, it's PVA, polyvinyl alcohol, polyvinyl alcohol. So if you take two vinyl alcohols, okay, let me show you. I'm trying to explain cross-linking here. Another application of cross-linking. It's applied in making slime. You must have made slime in high school. So if you take glue, which is a polymer, okay, take your glue, polyvinyl alcohol, which is a polymer, and react it with borax. So this is what you end up with. So if these are the two polymers from the top and the bottom, okay, these are the two polymers of the alcohol. If you add borax, the boron of borax goes in between. Borax is simply BOH. I think BOH3. If you add it, it's gonna add in between the two polymers of the glue, up and down, brings the two polymers together, okay, like a sandwich. And then the boron of borax, borax is used in laundry. The boron in the borax, this boron in the borax goes in between, linking the four OHs in the two polymers. So you get a cross linkage. It's because of this tetra cross link that slime will be slippery and will be stretchy. So, so for slime, it's gonna be stretchy because these OB bonds can be stretched. But if you have carbon-carbon linkage, those are very, very strong. Okay, so you don't expect it to be stretchy. You don't expect such a compound to be stretchy, although you have the cross-linking, because carbon-carbon covalent bond is stronger than OB bond, which makes slime stretchy. So if you want your polymer to be rigid, then cross-link it with a hydrocarbon. If you want it to be stretchy, then cross-link it with boron and oxygen, as in slime formation. Okay. All right. The flexibility of a polymer is in part also determined by the size of the groups on the vinyl monomer. I keep reminding you, vinyl looks like that. This double bond with a double bond, the pi bond between two carbons. That's called a vinyl. So larger groups on the vinyl will cause the polymer to be less packed. Larger groups, there's less packing, which means there is weak intermolecular forces. Okay, so for example, if you are to compare styrene versus PVC, the side chains that provide stronger dipole interactions increase the IMFs. So can you tell me, between styrene, polystyrene, and polyvinyl chloride, which polymer do you think will be having high intermolecular forces? Okay, which one? Of course, PVC will have high intermolecular forces. Styrene is used to make styrofoam. Can you apply pressure on styrofoam and press it? Yes. That's why when you receive your electrical equipment like a TV or a radio, you like playing with the packaging material by pressing them because they can be pressed and compressed, right? So styrofoam does not have a lot of strong intermolecular forces. In fact, what you have are weak London forces. And let me show you what polystyrene is, which is styrofoam. Polystyrene. So polystyrene is simply made from styrofoam. Okay, follow me closely. I know this chapter is too much of stories, but anyway. It's organic chemistry. So here you have a benzene ring, which I will call pH. So that's styrene. If you were to make polystyrene, you combine many of those. I'm going to show two monomers. I'm going to show two monomers of styrene. So if you were to stack this to another polymer, bring a second polymer here. Remember the pH is just the benzene ring. pH is just the benzene ring down here. If you are to stack them, all you have is hydrocarbon. So in between these two polymers, the intermolecular forces, IMF, intermolecular forces in there are weak van der Waals forces, otherwise called London dispersion forces. But in PVC, okay, this is not PVC, this is polystyrene or styrofoam. Okay, styrofoam up and down, or polystyrene. So if you are to consider the structure of PVC, polyvinyl chloride, which is made from vinyl chloride, the polymer, if you have N of this, the polymer will have this structure, Cl, Cl, and it repeats so many times, N times, just like this one would have repeated N times. So bring another polymer of itself on top, because we want intermolecular forces, so we have to bring the two together. So you remember chlorine is more electronegative than carbon. The chlorine is more electronegative than carbon. Dipole moments will point towards the chlorine. That gives you a partial positive charge on the carbon, partial negative on the chlorine. So here you'll have partial positive, partial negative. So you can imagine the partial negative chlorine will get attracted to the partial positive carbon of the second molecule. So intermolecular forces in between this polymer, okay, the intermolecular forces in between this polymer will be dipole, because you have dipole on top and you have dipole right here at the bottom between the C and the Cl. So it's dipole. Dipoles are stronger than weak van der Waals forces. So now coming back here, we'll say side chains that provide stronger dipole interactions will increase the intermolecular force and make the plastic harder. So that's why PVC, polyvinyl chloride, will be harder than styrofoam or your packaging peanuts, because dipole intermolecular forces are stronger than the weak van der Waals dispersion forces in the styrofoam structure. Okay, so the side chains usually help. And again, we said larger groups tend to cause the polymer chain to be packed less tightly. Phenyl group is a large group compared to the Cl. Okay, the softness is determined by the size of the group. Okay, I think that's clear. So we've talked about the physical properties, but before I talk about the cationic polymers, I'll talk about, in relation to the intermolecular forces, I'll talk about melting point. So the stronger the intermolecular forces, so let me summarize. The stronger the IMFs, the higher the boiling point or melting points. Okay? So that's very important for you to know. Now, if there is no dipole whatsoever, you expect your polymer to be nonpolar. Okay, so for example, styrofoam will never dissolve in water because water is polar. Styrofoam itself is nonpolar because the monomer is nonpolar. You see, all you have here is carbon hydrogens. Hydrocarbons are nonpolar. They are nonpolar covalent structures. So styrofoam will never dissolve in water. If it were to dissolve in water, then how will you be drinking juice during your birthday in your styrofoam cups? Or how will you be holding your soup on the styrofoam plates? So styrofoam or styrene or polystyrene will dissolve in nonpolar solvents like hexanes, okay, or like toluene. No, toluene is just a benzene with a CH3 on it. It's also nonpolar, like dissolves like, but styrofoam will never dissolve in water because water is polar, styrofoam is nonpolar. Okay. All right. Cationic chain growth polymers. So this is the polymerization where you have to go through formation of a carbocation intermediate, preferably a tertiary carbocation. Remember what we said. Tertiary carbocations are more stable than secondary. Secondary are more stable than primary. The reason being, if you have carbon containing R groups, they will tend to donate electrons towards the plus charged carbon, neutralizing it. So this is tertiary, where all these R groups are carbon containing substituents, and this is secondary. You only have two R groups, and of course primary will only have one R group. Okay, so in this case you will have two hydrogens. So that's primary carbocation, secondary, and that's tertiary. Okay, so the best the best vinyl for polymerization is the one that will go through a tertiary carbocation because that's more stable. For example, isobutylene. This is isobutylene. It's called iso because there's some sense of symmetry. You can cut the molecule into equal half. Okay, but let's talk about the carbocation. So I think there's a mechanism. So you see, you have a carbon here, a carbon, a carbon, a carbon, 4 carbons. So it's butyl, but you have a double bond, so butylene. But again, the whole structure is isomeric. So so we can polymerize this structure easily through formation of carbocations. So the best one that we've learned so far is Markovnikov addition. So you can use an acid catalyst or these Lewis acids. You can use Bronsted acid like HCl or the Lewis acids like AlCl3 and BF3. So preferably H plus for you because we've learned about that. So let's do Markovnikov addition. We said whenever you're adding an acid across a double bond, it's gonna do so following Markovnikov rule. Markovnikov rule states that the electrophile of the acid, which happens to be the proton, should go or end up onto the sp2 carbon of the double bond that has more hydrogens. So in this case, if I accept this hydrogen, it's gonna go onto this carbon because at least it has two hydrogens. This carbon does not have any hydrogen. So the red hydrogen will go where you had more hydrogens, which is the carbon to the right. So you make a CH3. So this is a CH3 now. And then the other carbon will be left with one bond less. You get a plus charge. So without showing the hydrogens, this is what the structure will look like. And it happens to be a tertiary carbocation. So that's what's explained here. So you do Markovnikov addition. The hydrogen goes where there's more, which is on this carbon. Now it's a CH3. You have a tertiary, not a third degree, it's a tertiary carbocation. Okay, that's the initial step. And then once you made your carbocation, the second monomer comes in. Goes here. This is your first monomer. Okay, so second monomer comes in, and it's of the same type. So really, we are still under addition polymers, because addition or chain growth polymers are made by this, are composed of the same monomer. So now this will be used, second monomer will be used as a nucleophile to attack the positive center. Okay, again, it's Markovnikov addition, because the electrophile ends up on a carbon that has more hydrogens, so which is this carbon. So you see, this is the piece that's just been added. Okay, so you have your CH2. Let's see, no, this is the piece that has just been added, this one, and then this was attacked. So if I were to circle the group, so this part right here is this part, okay, and then this molecule right here is this molecule here. So this played the role of a nucleophile. The other one circled in red played the role of an electrophile. It's attacked by the nucleophile by Markovnikov. Okay, Markovnikov addition, which states that the electrophile should end up onto the sp2 carbon of the alkene that has more hydrogens, which happens to be this CH2. So this CH2 accepts the circled group in red, which is this. Now this carbon right here will be that carbon right here will be one bond less, so it bears a plus charge. And then a third monomer will come to be added. So it's still addition, chain growth, polymerization. So this is the third monomer. It does the same Markovnikov addition. Okay, let me use a different color to circle it. So this piece will end up being this piece right here. Okay, so this attack that's shown here is just the same attack repeated down here. It's the same thing. So what's shown down here, it's the attack being shown here. It's just repeated. There's the mechanism is repeated. So use this third monomer, all right, to attack what already has the two monomers in it, but it has a plus sign. It's still a carbocation. You attack it. So this carbon right here will bear plus charge, which is what you have there. So now you have 3 monomeric carbocation. So the question is, will it stop? No, the fourth monomer will come attack, fifth monomer, up to the last monomer. Okay, so when the reaction is done, so you've done these attacks, Markovnikov addition, mechanism of addition several times, maybe n times, or n plus 2 times, or n plus 1 times. It doesn't matter, let's just say n, because n, the number would be bigger than just a 1, so we just say n. So if you want to stop the mechanism, we'll have to use a base. Okay, the base will take out this hydrogen. You make a double bond by a process called E1. So you'll make a double bond here, and then the base will be a BH. So if this is water, if water takes that out, then you're gonna get H3O plus. Okay, it gives you the double bond, and that's how the reaction would stop. So such polymers, the cationic chain growth polymers, are used as additives to lubricating oil, like what you use in your engines. They can also be used as glue or adhesives or inner lubes. Okay, so the next one is anionic chain group polymerization. So we started by talking about radical polymerization in the premiere video. I just finished explaining cationic polymerization, and now we are talking about anionic chain growth. It's used for vinyl monomers with very strong electron withdrawing groups, okay, such as a cyano group. You know, electron withdrawing groups will help to remove electrons. For cations, for carbocations, we want something that donates electrons towards the C+, right? That's why we say the tertiary cation is stable. For anions, for carbanions, you want something that will you want substituents that will take out the electrons, because here in this case we have too much electrons. That will stabilize the carbanion. So they are opposites, because this is an anion and this is a cation. Cation will need you to give it electrons to be stable. For example, in tertiary cations. Here, anions will want you to take out the excess electrons from the central carbon. So you need electron withdrawing. You need electron withdrawing groups, such as a cyano group, which is just C triple bond N. Okay. Also, an ester group can help remove electrons from the carbanion. So let's say this was a carbanion center, or this was a carbanion center. Or even phenol aromatic ring will help to stabilize it, and a vinyl can also help to stabilize the carbanion. Okay. You need an initiator, which can be organometallic compound. For example, an alkyl lithium. No, lithium will be positively charged, the R will be negative charged. Okay, which acts as a carbanion. You'll need that. So let's see what I mean. So the alkyl lithium is right here. You need it to start the process to make the first carbanion of your monomer. Okay, you'll need the organometallic alkyl lithium. So let's say, for example, you have CH3Li. That can be written as CH3 with lone pair negative charge and Li plus. So this R group is a alkyl group with lone pair and negative charge. So use that lone pair in your R group, for example, this lone pair, to attack the carbon of the vinyl. Is some sort of SN1 attack. So you'll attack this carbon, the pi bond opens up, so these two electrons are donated to the carbon. Okay, these are not fish hooks, they're double arrows. So you have a lone pair there. Now this lone pair can be sucked in by the cyano group. So this is the cyano. So we need electron withdrawing groups. And then this can be used to attack another monomer like this, and the chain will go. So the catalytic initiator adds to the alkene. Okay, the catalytic initiator happens to be the alkyl lithium. For example, methyl lithium. It adds to the alkene. Of course, you are seeing here the addition, which is then stabilized by resonance to the electron withdrawing group, which is Cn. For example, let me show you the resonance we are talking about. So assume this is your lone pair and you have your Cn. You know there's a triple bond in there. So this lone pair can be taken in towards the electronegative nitrogen, and then this can go up. So you get your resonance contributing structure, of which you'll have a double bond, and then you'll have your C, a double bond, and N. Now the N has two lone pairs, has to be negative. So these two structures are resonance structures. Okay, so the Cn helps to pull electrons towards it, as shown with these arrows that I've explained here, how the lone pair can be pushed towards the nitrogen. So you want that. You want electron withdrawing groups for carbanions. So that's initiation step. You made your first your first carbanion of the monomer, and the first carbanion of the monomer now can take the second monomer as we add onto the chain and making the chain long. So you use the lone pair of electrons, attack the carbon, and this opens up. So this is the piece that has just come in. That's what has been added, and the electrons fall on the carbon bearing the electron withdrawing group, which helps stabilize it. So now you have two monomers in this chain, and the process can happen n times, okay, until you end up with your polymer. Okay, remember this CH2 is this CH2 right here. This CH is this CH right here. The monomer is repeated n times. So that would be the polymer made by anionic chain growth. Now, as you continue, you make the last carbanion, and then you can quench the reaction. To quench is to stop, by just adding an acid where the negative charge on the last monomer that was added will accept a proton. Water falls off, okay, after acidic workup. So this is what we call acidic workup. So now you end up with your polymer, of which I represented it like this in the previous slide. We just usually show one monomer. N is the number of times the monomer is repeated in the structure. So you quench the reaction with aqueous, acid, water, or an alcohol. Those are proton donors, and the reaction will stop there. Okay, that's how you quench to stop the reaction in the terminal step of the mechanism of anionic chain growth, polymerization. Okay, so in the next video we'll talk about the stereochemistry of polymers.